Have you ever looked up at one of those massive, glowing LED billboards and just marveled at how perfectly seamless it is? I mean, it looks like a single, flawless sheet of light, right? But the reality behind that illusion is a pretty fascinating journey. It starts with heavy steel and concrete and ends with some microscopic, pixel-perfect software calibration. Welcome to today's explainer, where we're going to break down exactly how this multi-batch adjustment magic works.
Okay, so achieving a stunning setup like what we're looking at here requires this crazy mix of massive physical lifting paired with incredibly delicate digital tuning. When you're assembling a giant video wall, you're almost always using LED modules from totally different production batches. And because of manufacturing variations, even modules made in the exact same factory are going to have these slight differences in luminance and color. If you were to just bolt them together and flip the switch, well, you'd end up with a really distracting, patchy quilt of mismatched screens. Not exactly the flawless look we're going for.
So here's our roadmap for today. We'll start with building the perfect display, look at physical installation methods, dive into why calibration is an absolute must, get into the weeds of multi-batch software adjustment, and finally, wrap up with how we achieve long-term stability.
All right, let's just jump right into parts 1 and 2. Building the perfect display and the physical installation methods.
Before we even think about opening our calibration software, we have to deal with the macro world first, right? We're talking steel, concrete, and gravity. For building integrated screens, wall-mounted installations rely heavily on the bearing capacity of the wall itself. This means you need a precise laser level and some seriously heavy-duty chemical bolts. On the flip side, cantilever setups, which are often hung right over walkways, require strict pull rope reinforcements and super careful headroom calculations, because let's be honest, you definitely do not want pedestrians getting a physical close-up introduction to your brand new display.
Now moving over to freestanding outdoor advertising, your structural rules are basically dictated by size. Single columns work perfectly for screens that are under 10 meters wide. But the second you cross that 10-meter threshold, you absolutely demand double or multi-column installations. And crucially, both of these setups strictly require intense wind resistance planning and integrated light sensors. It's a major engineering feat before a single pixel even lights up.
Moving right along to part 3, the need for calibration.
Okay, picture this. The hardware is up, the steel is totally secure, and you send power to the wall for the first time. But the screen looks completely patchy. Maybe one section is slightly bluish compared to the rest. This is exactly where color matching comes in to save the day. It's the precise process of adjusting your LED panels to produce identical colors when fed the exact same signal. Remember, LEDs are physical diodes, and even within the same exact production batch, they act slightly differently. Without this step, your pristine, expensive display is going to have some highly visible, really distracting seams.
To solve this patchiness, the industry uses a two-pronged approach. First up, we have factory calibration. This happens at the module level before shipping, literally burning pixel-by-pixel correction data directly into the hardware's memory. But here's the thing, that's just not enough for a massive wall. You always need on-site calibration. This happens post-installation, adjusting the entire system to compensate for the physical environment and ensuring uniform harmony across cabinets that might have come from entirely different batches.
Which brings us perfectly to part 4, multi-batch software adjustment.
This is where software acts as a total rescue mission when your hardware batches are clashing. Understanding grayscale is absolutely key here. It's basically the number of discrete brightness levels a pixel can display, which is determined by the bit depth. If one batch processes these steps differently than another, the resulting image looks super jarring. So, we use gamma curve correction to mathematically force them into alignment. Think of it like this. If batch A naturally has a gamma response curve of 2.2 and batch B is at 2.0, the software literally wrestles batch A to perfectly match that 2.0 curve so the human eye can't tell the difference.
The methodology here is super strict. First, you have to normalize brightness to the darkest batch. Let's say batch A hits 1200 nits, but batch B maxes out at 1100. You actually scale batch A down to 1100 so they match seamlessly. Next, technicians use tools like a colorimeter to measure and align the color temperature, adjusting the RGB gain to hit a standard 6500 Kelvin white balance. So if batch A is running a bit warm at 5800K, the software increases the blue gain to get it to 6500K. Finally, the control system carefully groups these cabinets into specific zones, so the software knows exactly which correction coefficients to send to which batch.
In industry-standard software, like Nova LCT, this isn't just guesswork, it's a really strict digital workflow. Technicians identify the batches in the tool, manually load the specific adjustment files, and hit Apply to send those correction coefficients to the receiving cards. But step 4 is literally the make-or-break moment. You must click Save to Flash. If you forget to burn these settings directly into the hardware's memory, the entire screen will just revert back to a patchy mess the second it reboots.
And of course, you can't just apply the settings and walk away to get a coffee. Verification is essential. Technicians will blast the display with solid screens of red, green, blue, and white to aggressively hunt for any uniformity issues or color shifts. This step catches some really disastrous mistakes, like accidentally applying the wrong calibration batch file, which can cause this bizarre neon-like oversaturation, or maybe over-adjusting the brightness downward until the display is just completely washed out.
That takes us to our final section, Part 5, Achieving Long-Term Stability.
Because here is the harsh truth about LED technology. Our work isn't done just because the screen looks perfect on day one. We really have to ask ourselves what actually happens when these LEDs inevitably age over time. How in the world do we maintain that flawless multi-batch uniformity when every single individual diode is slowly degrading at a slightly different rate?
Well, to combat this physics problem, we turn right back to the digital realm. Advanced control systems run constantly in the background, using these brilliant aging compensation algorithms to mathematically offset the diode degradation. Operators also rely on periodic on-site recalibration and keeping solid logs of calibration coefficients. This is especially vital for advanced applications later on down the line, like if you need to swap in a replacement module or expand an existing screen with brand new mixed pixel pitch hardware. Plus, the system continuously uses light sensors for automatic brightness adjustment, ensuring the screen is never blinding at night or completely washed out in the midday sun.
I want to leave you with this thought. A perfect LED wall isn't just built, it is continuously calculated. The next time you look up at a giant billboard or a massive concept display, I hope you appreciate not just the heavy steel holding it up, but the relentless, invisible digital labor keeping millions of pixels in perfect harmony. But it does make you wonder, if software is constantly working overtime to hide the physical degradation of the hardware, at what point does that digital illusion finally break? Thanks for joining me on this explainer, and definitely keep your eyes open to the technology shining all around you.